Hi, everybody. I'm James Wexler, a software engineer at Google on the PAIR team, People Plus AI Research. I'll be talking about the Language Interpretability Tool, which is used for interactive analysis of NLP models. Now, the People Plus AI Research team I'm on, our goal is to make the partnership between humans and AI more productive, enjoyable, and fair. You can find us at pair.withgoogle.com. We're a large cross-disciplinary team at Google with a bunch of different roles on it. So software developers like myself, along with research scientists, both research scientists that specialize in machine learning, but also HCI, human-computer interfaces, interaction designers, visiting professors from universities and researchers, UX researchers, and more. So it's a great team that's very interdisciplinary, which really helps with our research. And the things we do can basically be broken down into three sections. First, conducting and publishing research on the interaction between humans and AI. Some examples of this are the People Plus AI guidebook that you can find on that website, which is a great resource for product teams looking to build AI into user-facing products, and best practices that we've learned and researched that can really help enable those experiences. We also put out a lot of different blogs on the research we conduct. Second, we create open source projects and tools to help with responsible AI practices. And that's where a lot of the work that I do falls into. Things like the Language Interpretability Tool, its predecessor, the What If tool, a TensorBoard embedding projector. These are all open source projects that can help with responsible AI in one way or another. And lastly, we try and widen just the range of people that can participate in responsible AI practices. So that means things like having a Medium channel where we do interviews and articles about research and different people in the field, and also building really interesting demos and educational resources like Teachable Machines, which is shown here in this slide, which is a great online resource for building your own machine learning models from just your webcam that can do fun toy things to kind of understand how machine learning works in abstract. But then also those models can be exported and used in real products down the line too. So let's step back and talk a little bit about responsible AI and what it means and why it's important. First of all, we can even just take AI out of it and talk about responsible product development. Now, we, meaning humans, have a history of making product decisions that aren't necessarily equitable to the needs of everybody. One great example of this is with car accidents. So in the US, historically, female drivers were much more likely to be severely injured in an auto accident. And a lot of this can be traced back to the decision to have basically male body type crash test dummies, as opposed to a variety of different body type crash test dummies. And this, one decision can lead to downstream effects that can cause more serious injuries in female drivers versus male drivers. And bringing it back to AI, another big piece is that enterprises, when they're building AI solutions, the biggest barrier between moving them from a research lab to a production environment where they're now user-facing is really trusting the system. So in addition to equitable treatment, responsible AI can also enable trust in your models by enabling debuggability, interpretability, and those types of things. Here's a basic overview of what an ML pipeline looks like for a standard supervised machine learning problem. You may have seen different versions of a similar chart before. Basically, I'm going through the different steps that are required to go through training a model and deploying it to production. And this is a pipeline where human bias can be introduced at pretty much every step. We start with collecting data. Now, the data you're collecting is based off of previous human decisions, and so it includes obvious bias from when it was created. Then often that data has to be manually labeled. So you might be taking a set of workers and taking things like, in the case of NLP, maybe you're taking sentences and labeling them with some sort of toxicity label. And there's humans doing that labeling work to create the ground truth for your model to be trained. And so bias can sneak in there as well. Then machine learning engineers are taking this collected data that's then been labeled and training a model to make future decisions on unseen data. And they're choosing different metrics to optimize the training for. And even the choice of those metrics introduces a bias that can affect the equity of the decisions being made by the model after it's been trained. That data is then used in some way in a product and then delivered to human. And that's another place where product decisions can bring in human bias. And then finally, an end user is going to use this, see an effect, and then have that inform their future decision-making behavior, which can cause more training data to be created, either for a new instance of that model down the line, or just new data if we're talking about data scraped from the internet, data that could be used for any number of different tasks from someone collecting more training data in the future. So we have this ML pipeline loop here where human bias can sneak in a lot of places, and it's important to be intentional and to think about all these different steps and use responsible AI practices at all these places in order to increase the likelihood of having a good model that's very equitable and fair. And you often hear people talking about human in the loop in AI, and often what they mean by that is that you'll want a human in the loop during any one of these phases. Maybe during training, you might want a human in the loop while your model's going through training epochs, looking at the model decisions being made and the way the decisions are trending, and maybe pushing the model in different directions, or maybe tweaking some parameters so that different outcomes happen. That's an example of like a human in the loop during training. What I think is actually key to responsible AI practices is having a human in the loop in this loop. So really all stages in this, having a human involved, understanding the data, not just looking at aggregate statistics and moving on to the next phase. And so in Pair, we try and build tools that help with all these different stages in the pipeline for having a human in the loop and thinking responsibly. Some examples here. One is the What If tool, which I'd mentioned before, which is kind of a predecessor to the language interpretability tool that I'm talking about today. We built it to be able to take trained machine learning models that either do classification or regression and allow you to probe them interactively and visually to understand what's going on under the covers and look at things like fairness, different treatment of different subgroups of the data, and if there's big disparities there, things like closest counterfactuals, what I have to change about a data point in order for the model to make a different decision. And so that's one version of a tool that's kind of built for evaluating trained models before they're deployed. Another tool we built is called Smiley, which can stand for a lot of things, but in my mind, it's always similar medical images like yours, which is for that stage when you're deploying to an end user. In this case, the end user is a doctor looking through pathology slides and looking for similar instances from the past to help make diagnoses. And this search that we built contains smart AI-driven elements that allow you to refine the search as a human, not just for similar looking pathology slides, but also with concepts that are really important to doctors, like maybe more tubular or more fused or different percentage of tumor glands. And they can tweak these things and have it affect the search in a way that's driven not by visual similarity necessarily in terms of pixels, but in terms of concepts that the model has learned. So it's a great way to put humans in the loop during model deployment and allow them to have some agency over what the model is actually doing. Now let's dive into the language interpretability tool itself. This was a collaboration between some of us on the Google Pair team, but also some in the Google language research teams that have a real specialty in NLP. When we were building LIT, the idea was to build a platform for interactive analysis and debugging of NLP models that can help lead to more responsible AI practices. But beyond that, to also be a conduit between research and production. So we're seeing a lot of amazing new techniques for NLP model analysis happening every month now. And we wanted to build a tool that made it easy for these research techniques to be built into a responsible AI platform that product teams can easily pick up without having to write their own adapters and read the research paper and understand how to implement it for their specific model. And that's really, I think, one of the key benefits of a system like this. Now, for some history, we started this project a little over a year ago in January of 2020. In August last year, we open sourced it. Since then, we've put out a paper at the EMNLP conference in November and launched our website with tutorials and demos, some of which I'll be showing today. And this year in 2021, we have a lot of plans to add great new features and take feedback from users and refine and improve the UI. So we can think of the language interpretability tool as basically a what-if tool for text, but taking the lessons that we learned from building the what-if tool and making a more extensible, a more flexible version that better meets product teams where we need to meet them for them to use the tool itself. When we think about why we built it, it's for a range of different stakeholders in the ML process, all the way from ML researchers that are maybe building new model types or architectures, or looking at new saliency techniques or interpretability techniques, all the way to the product suites that are actually taking trained models and building them into products to ship to end users. Along that whole range of different stakeholders, they all want to understand model behavior. And in NLP models, that often means counterfactual debugging. How does this model change if I make some change in the inputs? And there's a lot of different ways to evaluate that. It could be as simple as having some sort of evaluation golden set that you're always using to check models for, because it has a bunch of interesting edge cases and majority cases and interesting subsets of data in it. It could be using local explanations, like looking at token-wise salience to understand which words were most important in a prediction of the sentiment of a sentence. Or it could be looking at the model internals inside, looking at embeddings and attention weights inside the model and understanding how different tokens affect the model's predictions at the next layer in the model. So some design challenges we have when building this are that NLP models come in many shapes and sizes. There's a lot of different output modalities, not just classification or regression, but also sequence-to-sequence models that do things like translation or article summarization, for example. So it's hard to build and find general tools because there's such different modalities. Also, a lot of interpretability techniques have different code bases, so it's tough to integrate them all into one place for one team to use. That provides a really big barrier for experimentation for product teams looking to analyze their models for responsible AI. Oftentimes you see offline pipelines and static results being used because it's easy to calculate on, if you have 100 million examples, you'll need to run something offline and then analyze it after the fact. But that can lead to a loss in a train of thought when you're trying to ask and answer questions really quickly and interactively, because you only have the data that you've run on in the past. You can't make a small tweak and run the model again and see what happened live. Also, text counterfactuals are hard. This is something we learned when moving from the what if tool to the language interpretability tool. And if you have an input feature that's a number, like an age of a person, and that's one of the input features to some model, it's very easy to take age from min value to max value and see how just changing that one variable affects the downstream decision of your model, whatever it does. But when you have words and you're trying to change from like hello to truck, there's not really an obvious smooth sequence to go between those two words. So it's a difficult problem, and you need a human in the loop to really solve that. So we built the language interpretability tool to try and do this all in a single tool. So some of the core features are that, as mentioned, we can do counterfactual generation, and it's important to be able to do this a number of different ways. So manually, you can take a data point and change the words in it and rerun your model and see what changed. But we also have the ability for there to be algorithmic generators that will automatically make edits to your data points and create new versions of them to compare them to. We ship with a number of these, such as back translation, which can translate sentences from your source language to a foreign language and back to do some form of paraphrasing, basically, automatic paraphrasing. But you can also build your own in Python and incorporate them into the tool. We do local explanations through salience maps and attention. So looking at things like integrated gradients to look at token-wise importance for decisions. Another important thing is aggregate analysis. So looking at across the whole evaluation set, how am I doing through metrics like accuracy and also confusion matrices? And additionally, if I want to slice by something like break my data set down into subgroups that I care about fair treatment between, I'd want to see those same stats across those subgroups. An important thing we learned from the what if tool is side-by-side comparisons, both in two different dimensions. One is comparing two models side by side on the same data. So I might have a model in production and a new model I've trained that maybe I think might be more fair. I'd want to be able to compare them live and understand on what examples they're most different and why. Additionally, side-by-side comparison is important to compare two data points in a single model for things like counterfactual understanding. So if I take a sentence and change a word, I want to see not only what did that change in the final prediction, but what did that change in terms of token-wise importance and attention and everything else. And the tool itself is highly extensible to different model types and also different frameworks. So it's not tied to TensorFlow, PyTorch, or anything specific. It's just if your model can be reached from the Python language or remotely, then you can use LIT. So let's jump into some demos. So these demos are all available on the LIT website. Here we're looking at a a binary classifier that's doing sentiment analysis. So the 0 class is for a negative sentiment sentence. The 1 class is for a positive sentiment sentence. And this is a data set of sentences from movie reviews. So the first thing we can see up top is that we have our data table of our 872 evaluation examples, along with the embedding projector view of basically a projected down to 3 dimensions, what the model thinks internally in the relationship between all the data points. Down below, we have our overall metrics like accuracy on our eval set and a confusion matrix. Now, if we take a single example, we can go ahead and look at its prediction. In this case, it was a negative sentiment in ground truth, and it was also predicted as negative sentiment. The model got this one right. And we can look at the salience maps here to understand through different techniques which tokens were important to the model's predictions. So here's some gradient-based techniques. We can also run integrated gradients and LIME, which is a black box interpretability method. We can see that the words bleak and desperate are very powerful in dragging the sentence down to negative sentiment, which is not surprising. We could go ahead and change our sentence, changing desperate to happy, and we can analyze this new data point and see that now we have a positive sentiment instead of negative overall, and we can see that happy is bringing this up as opposed to pulling it down. It's kind of battling bleak versus happy to see which one wins out. In this case, happy is winning out, and we're getting positive sentiment. As mentioned before, we can algorithmically generate counterfactuals. In this case, we'll look at the word replacer generator, where basically we're asking it to find all instances of the word great, replace them with the word terrible throughout an entire eval set. We find 12 of those. Then we just easily, with one button, add those to our data set, and now we have 12 new examples added in. In addition to doing comparisons kind of live in the browser between the ones we created and the new counterfactual versions, we can, of course, also look back at the metrics and see now we have this group of paired metrics. So we have 13 pairs of examples now, originals and counterfactuals. And we see that, for example, we have a swap rate of 15% here. So 2 out of the 13, when we change great to terrible, actually caused a flip from one sentiment to the other. So that's an interesting thing we could dive deeper into if we had more time. Going over to another demo, this is not classification or regression. This is a text summarization model, so sequence to sequence based on the T5 model architecture. So in this case, we're taking a large input news article, basically, and there's a target summarization of that same large text. And then the model itself is trying to do its own summarization, and we can compare what the model's output is to our expected output to see where the differences are. In this case, we can also do next token prediction as well to understand in the input sentence how surprising each token is to the model, because that can be really important in understanding how well the model understands a given input sentence and it's going to do on its output. One thing we built in for this demo is a different kind of counterfactual generator, which actually looks through the training data that we've indexed offline to look for the most similar training data points to any given point in our eval set that we want to look at to understand what training data may have affected this prediction output-wise. And we can just click apply here. Now we get 25 nearest neighbors in the embedding space from the training data to this eval data. So that's another great way to do model analysis, not just by looking at token-wise salience, but also looking at examples that were really important to prediction. Jumping back to the slides, this briefly shows how the Language Interpretability Tool works. As mentioned, all the big number crunching is done in Python, where we define our models and data sets, interpreters and generators, and the front end is basically displaying that with some shared state. It's very simple to bring up once you define your models and data sets. To define a custom data set, it's super simple in Python. Here's one for a CSV file of restaurant reviews for a binary classification problem. We just need to define a spec, which gives semantic types to everything we're going to see in the data set. In this case, we have an input text, which is just a text segment, and we also have a ground truth label, which is 0 or 1. And then all we have to do is load input examples with this format into a member variable. And similarly, for the custom model that we want to use with lit, we need to define the input spec to the model, which is very similar to the data set spec. In this case, it's identical. There's an input text, and there's also an optional ground truth label. An output spec, which defines what the model is going to return when given the input. In this case, this model is returning multi-class predictions for the classes 0 and 1. Now, here's where if you wanted your model to also return things like attention and gradients and embeddings, you would also define them here as outputs as well. And then a predict function that takes in the inputs and returns back a list of dictionaries containing everything in the output spec. And that's all you need to do to be able to run your own model and data set in the lit tool. So thanks a lot for listening to this talk. I'm happy to take questions, and also check out our websites, both for the LIT tool itself and for PAIR in general. Thank you very much.